Hi, everybody. Welcome to section 3.3. This section is applications, uninhibited, and limited growth models. So let's just go ahead and get started. What I want to talk about, consider a function such as f of x equals 7e to the 5x. One thing that's going to be unique about this, if I take the derivative, f prime of x, what I'm going to get, remember I get the constant multiple back, I get the entire exponential back, e to the 5x, but then the chain rule says times the derivative of that exponent, the 5x, so the derivative is just the 5. But what I really want to point out about this, if I move that 5 out front and then say times 7e to the 5x, notice this 7e to the 5x is the exact same as what I started with, 7e to the 5x. So what I have is 5 times f of x, the original function. So f prime of x ended up being some constant times the original function. Now what's unique is that the only function that does this, again, other than the function 0, the trivial function, is this e to the x function. So we're going to use that fact to do some problems. So think about a business application where you're growing at a certain percentage every month, every year, whatever it is. That would be easy to model a function. I'll show you what I mean. Suppose our growth rate is, let's say 12%, just so that we have a nice number. If our growth rate is 12%, that means the next month, let's call it the next year. I think that might be a better way to say it. 12% per month would be an awfully big growth rate. So next year, we're going to have 12% of whatever we currently have. We'll call it P of X. Maybe it's our profit. So we've got 12% back of what we just did. Well, so let's say this. We start with P of X. If we start at P of X and we grow by 12%, that 0.12 P of X, that is our growth, total growth. Well, that's our growth. Think about where I'm going here. That's my rate of change. What do we know is the rate of change? Well, that's the derivative. So in this case, what I could do is I could say the derivative, if it's P, I could call it P prime of X. The derivative would be 12% of whatever I started with. Well, it's easy to see if I have a growth rate of 12%, but from what we just did, the way I started this, is the only way this can happen is if our original function P of X was some constant times e to the 0.12x. Let's see if that makes sense. So let's do a quick check. If I do P prime of X, think about what I get back. I get back all of this c e to the 0.12x, but then the chain rule says times 0.12. Well, this 0.12 is times all of this, but again, that was my original function. Oops, I don't want to write it that way. I want to write it as the original function. So it's 0.12 times P of X. Well, what is this? It's exactly what I have right here. And that's what we said the derivative was. So in general, they generalize this, of course, And what they say, let's use the notation that the book uses. So if we've got, let's put it in two different forms. We'll use Newton's notation and Leibniz notation. So if we have the derivative f prime of x, so here's Newton's notation, is equal to some constant k times f prime of x. Or if we put in Leibniz notation, remember Leibniz is dy dx. So if we have the derivative of some constant, this time we're going to say y, because y equals f of x. Ooh, I put an f prime here. I just meant to put f, because this f of x is the same as that y. So we're saying the same thing. This happens if and only if, means it goes in both directions. If and only if y is equal to some constant times e to the kx. So this k up here, this growth rate, is this growth rate right here. I'm going to erase that because we want to be able to see just the formula itself. Oops, that one I wanted to have over here, y equals c e to the kx, so that we're in Leibniz notation. And this one over here, I just wanted to change this instead of y equals to f of x equals. So f of x, the function itself, c e to the kx. Both times notice they're the same thing. We just either say f of x if we're in Newton's notation or y if we're in Leibniz notation. All right, so those are those. Now what I want to point out, this c right here, all we've said so far is it's a constant. We'll point to both of them. But the constant we're talking about, well, here, let's say this. What is this constant? Well, suppose at time t equals, we're using x, at time x equals 0, we have, let's just make up a number, 20. So what I would do, so coming here, my f of x equals c e to the kx. I'm going to say, okay, it's 20 when I have c e to the k, whatever k is the growth rate. I don't even need to know it yet, but I know x is 0 times 0. Because what's going to happen? This is going to be c e to the 0 is 20. Well, 20 equals c, anything to the 0, except 0 to 0, of course, is 1. So I just get 20 equals c. Okay, at x equals 0, this was my initial amount was 20. So that's always, always, always the initial amount. So we'll say note the constant c is always, lift that up so I don't write down there, the initial amount of the function. And I'll show that in an example very quickly. All right, so I'm just documenting that. All you have to do is remember it. You don't have to build up to that, but we'll see that as we do one of these problems. And in fact, we're going to do one of the problems right away. All right, so I'm flipping through the book and I am going to, it's problem 8 and it's on page 331. All right, here's what it says. It says franchise expansion. Pete Zaz Incorporated is selling franchises for pizza shops throughout the country. The marketing manager estimates that the number of franchises N will increase at a rate of 10% per year. So let's write that down. That's very important. Number of franchises N that's not very good N. Let's write that a little bit better. Will increase at a rate of 10% per year. Now, a lot of times we do calculus on things and they give us some sort of function, and then we do things like take the derivative, find max and min, things like that. But notice this time they're telling us how quickly something grows. Well, it's increasing at a rate, they're telling us the derivative. I'll say, look, that's the derivative. So in fact, one way we could write this, we could either write in notation dn dt. So the rate of change of n with respect to t is 10% of whatever n was. You could always write that in Newton's notation as well if you wanted to, or we could write it as n of t, since it's the derivative, it would be n prime of t equals 0.10 n. And I wrote it as 0.10 n instead of just 0.1. You could write it either way, but the 0.10 looks more like 10% to me than 0.1 does. So you may see that either way. Either way that it's written is fine. But from what we talked about earlier, the only time that the derivative, notice the derivative of n, that's what we're having here. This is, we could call it d dt of n. It's the derivative of n. And if the derivative of n is some constant, this time 10% times n itself, it must fit that exponential form. So because it fits that form, we know that n has to be, and we'll write it as n of t, has to be some constant times e to the kt, but in this case, that 10%, that is k, that's my growth rate. So it's e to the 0.10 t. And I've got my function immediately. If it grows as some constant times the original function, it has to be this exponential. All right, so that's where we are. So we know that, we know what the function looks like. They go on and they tell us some more. They say this, part A says, find the function that satisfies the equation, assume the number of franchises at t equals 0 is 50. Find function n, it's supposed to be a C, find function n given that n equals 50 at t equals 0. This is my initial value. N equals 50 is initial value. That's what we were talking about before. In other words, C equals 50. So I can just plug that straight in. I know n of t, here's my function now, 50 e to the 0.10 t. There's my function. And I built it straight out of just knowing what the growth rate was. Now, again, if you're having trouble believing that that's what C is, you could always say, okay, if going back here, here's my little proof. If we had n of t was C times e to the 0.10 t, and we know that n of t is 50 when K equals 0, oops, I wrote, no, that's a T. When T equals 0, so we'll say times 0, we'll notice that's C e to the 0, which is C times 1, which is just C. So C has to be 50. Again, you don't have to prove that. You can just remember that this value C, that's my initial value. And this number here, K, is the growth rate. Oops, let's erase that. All right, so we've got our function. We'll do another one similar to this. I'm looking and I don't see that we are doing one similar to this. So maybe we will, maybe we won't. We'll probably do one real quickly just to make sure that we understand what's going on. So part B says, how many franchises in 20 years? How many franchises in 20 years? Well, that just means T equals 20. Now it's just a calculator problem. So I'm going to go, well, the number after 20 years is 50 e to the 0.10 times 20. Now, in some calculators, when you do e to the power, it actually puts it up as an exponent. Sometimes it just says e to the power. If that's the case, you have to make sure you put the power in parentheses. Otherwise, e will just go to the 0.10, and then it'll multiply that answer by 20. Because remember, order of operation, exponents come before multiplication. But stuff in the parentheses comes before exponents. So I'm going to enter it that way. I'll actually show you how to do this one. Let me jot that value down real quickly so I make sure I enter the correct thing. All right, let me flip over to my calculator. Here's my calculator. So I'm going to find, all I need to do is 50. And then e to the power, I go second. The ln button is e to the power. Now notice mine actually puts it as an exponent. If it didn't, I would have to do parentheses, 0.1 or 0.10, I'll put it the way we see it, times 20. And you can close parentheses or not, it doesn't matter. I'm just going to hit equals at this point, enter. That's my value, 369.45, which we're talking about franchises. I'll round to the nearest and say about 369 franchises. So we'll say about 369 franchises. All right, there's a part C to this as well. Part C says, in what period of time will the initial number of 50 franchises double? All right, let me point this out to you. Now, there's a formula for this. I'm going to go ahead and just show you the formula right now, and then I'll show you where that came from. Doubling time. You are welcome just to remember the formula. The doubling T, all right? The formula is the doubling time T is equal to the ln of 2 divided by whatever the growth rate K is. And if you remember that, you can just use that formula. So in our case, I've got the ln of 2 divided by K, which was my growth rate. Well, my growth rate was that 10% per year. Remember way up here, they said they grow at 10% per year. It's the same K value that I was using here, but ln of 2 divided by 0.1. Again, I'll go ahead and go to the calculator for this. So I've got ln of 2, make sure you close the parentheses, divided by 0.1 or 0.10, and I get about 6.9 years. Now, I'm not going to round that to the nearest year because we can have part of a year. So about 6.9 years. Now notice that's not 6 years and 9 months, it's 9/10 of a year. So it can't be months because obviously there's 12 months in a year. If you wanted to know how many months it is, you could multiply that 0.9 by 12 months and get it closer to the month. We'll just leave it at 6.9 years. So doubling time approximately 6.9 years. All right, so let me show you where that formula came from. That's the end of that problem, by the way. Now notice we didn't do any derivatives there. It was the idea that they gave us the derivative. So when they told us that the growth rate, 10% increase, that says, oh, it's 10% of n, which was the derivative. We're going backwards to find the only thing that fits that, which is that c e to the kt formula. All right, but let me show you that doubling time formula. We'll say, where does doubling time come from? We'll say doubling time formula come from. Oops. We'll try to say doubling time formula. There we go. All right, so there's my question. So let's suppose we have, and we can pick any number we want to, and in fact, let's just say n. Suppose we start with n how long until it doubles? All right, so there's our question. Well, let's say this. Now, so we've got n. Let's say this. We know it's, don't want to use n there. Did we use n up here in our formula before? We used f of x. All right, so let's do this. So we'll write it as f of x. F of x equals, we know it's some constant times e to the kx. Okay, there's our formula. Well, if we've doubled, we started with n, so that means c was n. E to the kx. I'm going to change this real quickly. Instead of x, let's call it t because we're calling it time t. So let me just erase that and that. We'll call this t because now it's the time, which is what it always stood for. But I've doubled. If I've doubled, I go to 2n. If I start at n and I double, now I've got twice as much. I have 2 times whatever I started with. All right, so there's my formula. I know n was what I started with, that's c, and then the e to the kt. It's doubled now, it's 2n. Well, to solve this, now I have to do a little algebra. I'm going to divide by n, that cancels this n, but it also cancels that n. And I get 2 equals e to the kt. Notice doubling time has absolutely nothing to do with where you started. If you're looking at money, if you have $1 and it doubles to $2, that's exactly the same rate and time as if you had $1 million and it doubles to $2 million. Doubling time doesn't change based on the amount, it's just based on the rate. That's why the amount canceled out. Now, the way we solve this is we take the ln of both sides. The reason we're taking the ln is because we're trying to solve for the variable t. It's up in the exponent, so it's an exponential function. I need to use a logarithm to cancel out an exponential. Well, the ln and the e cancel each other out. They're inverses. We just get k times t equals the ln of 2. And then to solve that for t, we divide by k. And we get doubling time k is ln of 2 divided by k. So there's my doubling time formula. Doubling time formula. Oops, get that out of there. Doubling time formula. Notice what we could do over here, we had this ln of 2 was equal to kt. If I wanted to figure out what k value, what growth rate I need to double in a certain amount of time, say I already knew the time and I said, hey, I want it to double in 5 years. What rate do I need? Well, I can take the same thing except divide by t. Now I have k is equal to ln of 2 divided by t. So this one's doubling time formula. That's how I'd find time. It's just ln of 2 over k. This one would be rate needed to double. We'll say in given time. So I use this if I know the time and I'm looking for the rate. I use the doubling time formula if I know the rate and I want to know the time. So either one, notice it's just ln of 2 divided by the other one. But that ln of 2 divided by t, that's what I was using right here. ln of 2 divided by k, that's t. ln of 2 divided by k, that's t. So that's where that came from. All right. Let's see. Let's try another one of these problems since I told you that we could do this. Well, here's one. I'm not going to do, on part B, it says estimate the net sales in 2012 and 2016. I'll probably just do one of those, but this is problem 12, just to make sure we get the idea of it. This is on page 332. All right, and it says annual net sales. Green Mountain Coffee Roasters produces many varieties of flavored coffees, teas, and K-Cups. Since 2008, the net sales of the company have grown exponentially at the rate of 46.3% per year. Wow. So growth rate, that is just an amazing growth rate. 46.3%. I don't know where that came from. 46.3% per year. This growth rate can be approximated by, now they're talking about S as sales. Well, this is the rate, so it's the derivative. So it's the change in sales over the change in time, the derivative. So the derivative of sales with respect to time is, if we change that, get rid of the percent sign, move the decimal 2 places, it's 0.463 times whatever the sales were. Okay, that's not a 5, that's a sales. That's my formula of the derivative. Well, since that's the formula from the derivative, it can only be true if it came from a function. S of t is whatever my initial sales were. We'll call them S sub 0. That's my initial sales, times e to the 0.463 t. They tell us, we'll put it up here, t equals years since 2008. Years since 2008. All right. Now for part A, they say find the function that satisfies the equation given that net sales in 2008 were approximately 500,000. So A, find formula given that sales equaled 500,000 in 2008. The same 2008 that we talk about right here. So T is years since 2008. Well, if it's in 2008, there's been 0 years. So that's my initial cost. That's my S sub 0. So my formula is just sales at time T, 500 e to the 0.463 T. Again, a very quick formula. That's the only formula it could be. since we knew that derivative was a constant times the function itself. B says estimate the sales in 2012. So we'll say sales in 2012. Well, what that tells me is time, 2012 minus 2008. So we're saying, oh, that's 4 years after we started. So I'm just trying to find S of 4. Now, I'm not going to flip back to the calculator. I'm just going to do this on my own calculator. You can flip back to see how we did it last time if you want to, but I'm just entering 500,000 e raised to the power 0.463 times 4. I should write down what I'm doing there. So this was 500,000 e 0.0463 times 4. Again, put that in parentheses if you need to. The answer should come out as, and I'm just going to go to the nearest dollar. What they asked me to do, they just went to the nearest dollar. So it's 318,627. And then it's 5.9, so I'll round that up to a 6, put a comma there, put a comma there. Just almost $3.2 million in sales after 4 years. That's how quickly things can grow with exponential growth. Notice it was only 500,000 4 years ago. Now they're up to almost $3.2 million in sales 4 years later. That's because we had such a huge growth rate of 46.3% per year. All right, now let's find the doubling time. Find doubling time. Oops, doubling time. Well, since we already worked on it, we'll just go straight to the formula. The time to double is ln of 2 divided by k, which in this case is ln of 2 divided by 0.463. And I do that in my calculator. ln of 2, close parenthesis, divided by 0.463, 1.497, about 1.5 years. So every year and a half, they double their sales. That is the kind of stock you want to invest in. All right, so again, we did another example, a pretty quick one. And there's a couple other problems in here I want to do that show, there's only one other one I want to show before I do the other thing. Remember, this is called, let's see what it's called. Where's my title? Applications Uninhibited and Limited Growth Models. This is the uninhibited because it's e to a power. So the reason this is uninhibited, remember e to the power looks like this. Well, it's uninhibited, goes up forever. This is y equals e to the x. Uninhibited growth. All right, that's the idea of the uninhibited growth. But there was one other problem I just wanted to make sure you knew how to do. There's problem 14, and it's also on page 332. But it says, Hardy Bank advertises that it compounds continuously and that it will double your money in 12 years. What is the annual interest rate? If money doubles in 12 years, what is the interest rate? Now it says it's compounding continuously. That's where they use the E. There's a slightly different formula you may remember from college algebra. If it's not growing continuously, if it just grows at the end of each month or at the end of each, there's a different formula I have to use. E is not the base, but E is the base if it's continuous growth. So remember we had for time, ln of 2 divided by k. We also had k is ln of 2 divided by t. That's what we're looking for. We're trying to find k, the growth rate. So we do ln of 2, and they just said it's 12 years. That's all we do. We just plug that in, we get our answer. So my growth rate, ln of 2 divided by 12 years, I only need a growth rate of it's 0.0577. So we'll go 0.0577. So we'll round that up to an 8, which is 5.8%. Doesn't take a really large growth rate to double in 12 years. But we can always find it. If you're saying, hey, I want to double my money in 5 years. All right, just do divided by 5. If you want to do double it in 10 years, divide by 10, see what you have to get as a rate of return. All right, that's the end of the uninhibited growth model, but we have another model that doesn't grow uninhibited. It's the limited growth model. So let's talk about the limited growth model. Let me show you a picture of what this looks like. So the limited growth model, typically what's going to happen, let's say we have something like this. What's going to happen is there's going to be some limit up here. So you can think of it as a horizontal asymptote. But the way the model works is you're going to start from some point, you're going to start growing, but at some point it's going to start to flatten out and approach this. That's what the limited growth model looks like. You start to grow and it starts to grow exponentially up to some point. See, right here, it's growing exponentially, but then the curve turns. And hopefully you recognize what that point is. It's an inflection point. All right, so we're going to look at this. The way this model looks is a little bit different. You don't have to remember what the model looks like. They will show you specifically in the problems what the limited growth model looks like. They'll give you the formula. All right, but let me give you the basic idea of the formula. The formula, they use this a lot in populations. For instance, we're talking about a rabbit population in a forest. Like, it can't get too big because it runs out of food. So they usually use P of T for population size, but it can be other things as well as populations. But it's it's L, over 1 plus B e to the negative KT. That's the general formula. Now, the 1 doesn't always have to be a 1. They do say K has to be greater than 0 because you're not going backwards. We're not shrinking. If K is a negative number, you're not having growth. The growth's not going to go up. It's going to go down. So K has to be a positive value for this to work. All right. Let me show you something about this real quick because we're going to use this. This piece right here. Consider B e to the negative KT. What that really means, that negative exponent moves it to the bottom, but it only applies to the E, it doesn't apply to the B. So I can rewrite that this way. And what happens as T goes to infinity, let's erase this. As T goes to infinity, that's not an infinity. As T goes to infinity, that's a little bit better. What's going to happen is that E to T also goes to infinity. All right, I need to rewrite both of my. There we go. Not great, but good enough. And this actually says as. Not real. Okay. T goes to infinity. E to the KT goes to infinity as well. And then B over over e to the kt goes to 0. Now that's always going to be the case. That piece is always going to go to 0 as t goes to infinity. I may show you with some numbers. In fact, let's just plug in some numbers right now. So say we had 5 e to the negative, let's say we have 6% growth, 0.06 t. Now that's equal to 5 over e to the 0.06 t. And I'm going to do a little chart. We're going to need a little bit longer chart than that. So I'm going to plug in some values for t, and we're going to see what happens to, and you could just leave it as negative exponent if you want to. When I write it divided, then we see, hopefully, why it's going there. But let's put that in there, and I'm just going to plug in some values. Remember, t is going to infinity. So let's do like 10, and we'll do 100, and we'll do 1,000. So t is going to infinity. You know, let's do it like I did in class. That's not what I did in class. Let's erase that. Let's say t, let me erase all that. So notice here, t is going to infinity. And over here, let's see what this goes to. All right, so I'm just plugging this into my calculator. So I'm going to go 5 e to the negative 0.06 times 10. And I get about 2.7. If I do it to the 100th power, I get about 0.012. And if I do it to the 1,000th power, I get, now it's a very small number. It's 4.4 e to the negative 26. So in fact, it's 0.000 ... 044, and there are in fact 25 zeros. So it's getting really, really close to 0. We'll say approximately 0. So the moral of the story is, coming back here, this piece is going to go to 0 as t goes to infinity. So this is going to give me my limit. My limit as t goes to infinity. All right, let that sink in for just a second. All right, so let's see where we're going with this. Let's go ahead and we're going to jump into an application where we're going to use these ideas. But I'm not going to go through the proof of the limit anymore because we just saw the limit there. All right. So here's an application here, and it's similar to one of the ones I assigned. It's problem 28. Let me tell you a little bit about 28. First of all, on page 333, but I've changed it because I want the wording to match the wording that's going to be very similar to your homework problem. Unfortunately, there wasn't one that really looked a lot like your homework problem, so I thought I would throw this in. All right, so let's see. I said it's problem 28. That is not the problem I wanted to do. Problem 42. Let's change this to a 42. All right. And this one is on page, so this one's very similar to 43. It's on page 335. But what it is I changed one of the numbers on here because it's wrong in the book. I guess I didn't have to tell you that, but if you're looking at the book at the problem and you say, that's not what they had, I changed it to match the answer. It's an even numbered one. You don't have the answer anyway, but I do. But the function is 3,400 divided by 17 plus 183 e to the negative, and here's what was wrong in the book. It's supposed to be 0.0982 t. And they just forgot that zero, the first zero after the decimal. In the book, it just says negative 0.982 t. All right, so here's what the problem says. It says limited population growth, human population. 17 adults came ashore from the British ship HMS Bounty in 1790 to settle on the uninhabited South Pacific island Pitcairn. The population P of T of the island T years after 1790 can be approximated by the logistics equation. And so this is P equals population, T years after 1790. All right, so part A says find the population on the island after 10 and 50 years. They throw in 75 also, but I don't want to do too many of these. They're all going to be the same. It'll be different numbers, of course. Find population after 10, well, here I'll show you. 10, 50, and we'll do 75 years. All right, so we just plug in. So I say, oh, P of 10. And I'll show you, it'll be pretty quick on the calculator. So it's 3,400 over 17 plus 183 e to the negative 0.0982 times 10. And for the next two problems, all I do is I change the 10 to a 50 or a 75. All right, so it's population. I'm going to round to the nearest. And you could say, oh, if I have 0.8, that's really not a person, but it's an approximation anyway. So we'll just round to the nearest whole number. All right, so let me show you how I'm going to get this. So let me go to the calculator. All right, so here's what we have. So it's 3,400 divided by, now I have to put the whole bottom in parentheses. Oops, too many parentheses. Let's go back and delete one of those. Okay, so it's 17 plus 183 E, so I have to go second E, so the LN button. And I'll put a parentheses here too again. I don't need to on mine because it shows it as an exponent, but yours may not. Negative, remember that's the negative button, 0.0982 times, and what do we do, 10 years? 10. So I'll close that parenthesis. I don't need to close the other parenthesis. I will, just so that it looks pretty. And then when I hit enter, I get about, let me jot this down on a piece of paper because I'm not going to leave this yet, about 40 people. What's nice about these TI calculators is I don't have to re-input all that stuff. I can just go second enter and everything I typed in comes back. And what I'm going to do is I'm going to arrow over to where this 10 is, and I'm going to change it to the 50. And now I hit enter. Oh, now I'm at about 185 people. And then I'm going to do it again, second enter, and I'm going to arrow over and I'm going to change that 50, oops, too far, to a 75. And I hit enter. Oh, I've got about 199 people. And so hopefully you can see the number is starting to get a smaller increase. I went in 25 years, I only went from 185 to 199. I only added 4 people. Now, remember that limiting factor we saw before? Let me show you this real quick. Suppose I change this, instead of 75 years, let's go to 1,000 years. Oh, look, 200 people. That's my limiting factor. I'll show you how we get to 200 in just a minute. All right, so let's go back to the problem. So I did this first one, and I got, what did I get? 40 people. So after 10 years, they had 40 people. Saw P of 50. I'm not going to rewrite everything, but we're at 185 people. That's not a very good E. Where's my eraser? There it is. And then P of 75 years, we're up to 199 people. All right, so that's part A. Part B says, find the rate of change in the population, P prime of T. Find rate of change of population. Now they say in the book P prime of T, but I would expect you already knew that it was P prime of T because it was a rate of change. All right, so now when I take the derivative, of course I have to use the product rule. All right, let's try the product rule. So let's go. So we have low D high. Remember the bottom, 17 plus 183 E to the negative 0.0982 T. So low D high, well, the numerator was just 3,400. The derivative of the top is just 0. So low D high, so this whole thing goes to 0 because you're multiplying by 0. So low D high minus high, 3,400, D low. Well, when I take the derivative of the bottom, the 17 goes to 0. We're going to run out of some room here. Plus 183. Remember, I get the whole exponential back, 0.0982 T. But it's times, let's make that a bigger parentheses, times negative 0.0982, that's my chain rule, all divided by the bottom, good heavens. That's a 0 there. Squared. All right, so let's see. This, it cleans up nice because that whole first piece went to 0. I'm going to multiply the negative 3,400 by the chain rule piece just to get that as a nice, times the 183. So negative 3,400 times 183 times negative 0.0982. And I get about 61,100. So the derivative, P prime of T, is about 61100. If I care, it's 0.04. And that's not rounded, that's exact. All over the, and then the rest of that, what else did I have? E to the negative 0.0982 T, all divided by 17 plus 183 e to the negative 0.0982 T, whole thing squared. Now be careful, I see this all the time. Students want to cancel that E on the top with the E on the bottom. We can't because of this plus right here. You can't cancel a piece of a term. Things added or subtracted, remember those are terms. You cannot cancel those e's. Don't do it. It won't turn out correct. All right, so anyway, that whole big old monster is my derivative. All right. So C, we're just going to do one of these parts. They say, find rate of change in population after 10 years. I will do 10 years and 75 years. Well, that's kind of an ugly function. Find rate of change. I'm just going to do one. After 10 years. All right. Now, here's what I'm going to have to do. Since that is a big ugly thing and I won't have access to it once I go into my calculator, because I want to show you calculator-wise how to do this, what I'm going to do is I'm going to take a quick picture of it so that I'll have the formula. All right, let's see. All right, so there's so I took a picture of it so that I can refer to it. All right, so let's go back to all right, so I've got it. So let's go to the calculator. All right, so I've got 61100.04. Now times, you don't have to hit times. You can just say e to the power. It'll do times. Again, put in the parentheses if you need to, negative 0.0982 times, and what are we doing after 10 years? All right, so that's the numerator. So what I can do, either hit equals, I'm going to do that, that's so much easier. So there's the numerator. The whole thing I'm going to do divided by. I don't have to re-enter the number, just hit divided by and it'll pull up the number for you. Now in parentheses, I've got my 17 plus 183 e to the negative 0.0982 times 10. Close parentheses. We need to square the whole thing. And so I hit enter and I get about 3.13. Let's round that to just 3.1. The reason is it's the rate, so it's p prime of 10. It's about 3.1, and the reason I rounded it just to 1 decimal because it's people per year. That's the growth rate. Because remember, it was the change in people over the change in time. So it was people per year. That's one of the good things about Leibnitz notation. It gives you the units real well. So after 10 years, in the 11th year, let's state that. In 11th year, we expect the population to increase by about 3 people. Now here I'd round to the nearest because again, we're talking about people. We're not looking at an average or anything. We're saying, well, what's going to happen next year? Yeah, we'll go up about 3 people. All right, again, be specific. That's in the 11th year. If it's the 12th year, if it's the 15th year, it's not 3 people. It might be 3 people since it was rounded off. But if, for instance, when they did it at 50 years, it was 1.3 people, not 3.1 people. And at 75, it was 0.1 after year 75. And then part D, which is our last part, find the limiting value on island. In limiting value, what that means is find the population when t goes to infinity. So again, remember, here's what we do. Let me write down the formula. We had P of t equals 3,400 divided by 17 plus 183 e to the negative 0.0982t. But remember, this whole thing goes to 0 as t goes to infinity. That's what we talked about earlier. So as t goes to infinity, P of t is approximately 3,400 over 17 plus 0, which is, of course, just 3,400 over 17, which is 200 people. Notice that's exactly what I got when I plugged in 1,000 years. Even at 75 years, we were at 199. Didn't grow much after that. That's the limiting value. It's always, remember, it's these two numbers, limiting value. All right, well, that's it for today. Hopefully that worked out. A lot of stuff. I'll make it up for you on the next video, because the next section 3.4, we don't do hardly any of it. It's essentially what we did today with the unlimited growth model, but it's decay. All right, so anyway, we're going to stop there. I hope you guys all have a good time with this, and hopefully this all works out for you. So work hard. Remember, you can get this.